On this worksheet, we're going to practice drawing molecules that violate the octet rule, which is actually pretty common. We're going to be starting with SO3. Let's begin by adding up the valence electrons in the SO3 molecule. Sulfur has 6 valence electrons. The oxygen in this molecule, we have a total of 3 oxygen atoms. They each have 6 valence electrons. That's going to be a total of 24 electrons for us to work with. We want to start by putting sulfur in the center. We know that it goes in the center because it is the first atom in the formula, SO3. And then we want to connect the oxygen atoms to the sulfur using single bonds. Those 3 single bonds each have 2 electrons, so that used a total of 6 electrons. We used 2, 4, 6 electrons to make those single bonds. It leaves us with 18 more electrons. We're going to use those 18 electrons to satisfy the octets for the outer oxygen atoms. Each oxygen atom currently has 1 single bond. That means it has 2 electrons. So we're going to give each electron 6, or each oxygen atom 6 more electrons so that it has 8. We used 18 electrons there to give all those oxygen atoms octets, so that means that we now have a total of 0 electrons to work with. Now, one of the tools that we have to help us decide whether or not we're allowed to violate the octet rule is formal charge. So now that we have this structure drawn, what we're going to do right off the bat is just start by calculating the formal charges of all of the atoms in the molecule. Now, you might be saying, hold on. The sulfur atom doesn't even have an octet yet, and I know that it doesn't have an octet yet. I'm just going to start by calculating formal charges because we're going to use formal charges to help us draw this molecule correctly. So for the oxygen atom, all the oxygen atoms are the same, a valence of 6, 1 bond, 6 non-bonding electrons. So all of our oxygen atoms have a formal charge of -1. All of them are -1. And the sulfur, which also has 6 valence electrons. This sulfur has 3 bonds. It has 0 non-bonding electrons. It has a formal charge of +3. So when we have an atom that has a negative formal charge like this oxygen, the negative formal charge just kind of in a way means that it has too many electrons. And when we have an atom with a positive formal charge, that kind of in a way means that it has not enough electrons. So what we want to be doing is taking electrons from atoms that have negative formal charges and using those electrons to form double bonds or triple bonds with atoms that have positive formal charges. So let's just pick on this oxygen on the top, and let's take one of its lone pair of electrons and let's move it in to make a double bond with the sulfur. Just like that. And when we do that, that's going to change the formal charge of this oxygen atom. It's also going to change the formal charge of the sulfur. So let's recalculate those formal charges. The oxygen atom is now 6 valence, 2 bonds, 4 non-bonding. That oxygen atom is now perfect. Our sulfur is now 6 valence electrons, 4 bonds, 0 non-bonding electrons, a formal charge of +2. So it's still not looking good. That formal charge is still pretty high. So let's work on it some more. Let's take some electrons from a negatively charged atom and use those electrons to make a double bond with a positively charged atom. Let's focus right here. We don't want to mess with this oxygen atom anymore because it's perfect. So let's take a lone pair of electrons from the oxygen on the right-hand side and use that to make a double bond. And when we do that, that's going to change the formal charges for both those atoms, the sulfur and the oxygen. The oxygen is now 6 minus 2 bonds minus 4 non-bonding electrons. The oxygen is perfect. The sulfur is 6 minus, it now has 5 bonds, no non-bonding electrons, formal charge of +1. We can do, I realize I left a negative sign over here, we can do this process one more time. We have one more atom that's negatively charged and one more atom that's positively charged, which means we could move electrons one more time to create another double bond. And we've seen this done 3 times now with the oxygen. So we know that this is going to leave that oxygen with a formal charge of 0. And our sulfur now has 6 valence electrons, 6 bonds, no non-bonding electrons, also a formal charge of 0. So this is the correct Lewis structure for this molecule. Even though sulfur is violating the octet rule, the formal charges are helping us know that it's okay to violate the octet rule in this case. Let's try this again with our next example. Aluminum trichloride, AlCl3. Aluminum has 3 valence electrons. The chlorine atoms in this molecule, we have 3 chlorine atoms. Each one has 7 valence electrons. That's going to be a total of 24. We want our aluminum in the center, and we want our 3 chlorine atoms around the aluminum. And those 3 single bonds used a total of 6 electrons, leaving us with 18 more. We're going to use those 18 electrons to work on the outer atoms' octets, and that is going to require 18 electrons, so that leaves us with none. Now, our aluminum atom does not have an octet, but before we decide that we want to make double bonds, let's calculate the formal charges and see how things look. The chlorine atoms are all exactly the same, and they all have a total of 7 valence electrons. They all have 1 bond. They all have 6 non-bonding electrons. They all have formal charges of 0. 7 minus 1 minus 6 is 0. So they're all good, and we don't want to do anything with those chlorine atoms because they're perfect the way they are. The aluminum has 3 valence electrons. This aluminum has 3 bonds, no non-bonding electrons, a formal charge of 0. So this structure is correct the way that it's drawn, even though aluminum doesn't have an octet. Let's just kind of pretend, let's just imagine that you didn't think about doing that, and let's say that you just thought, oh, I see this aluminum doesn't have enough electrons, I'm going to give it a double bond, I'm going to do it like that, and this was the structure that you came up with. You could still be okay as long as you calculated formal charges. So if you calculated formal charges, I shouldn't have erased these ones. 7 minus 1 minus 6 is 0. If you calculated formal charges from this structure, aluminum has 3 valence electrons. This aluminum has 4 bonds. That's a formal charge of -1. And this chlorine, 7 valence electrons, 2 bonds, 4 non-bonding, formal charge of +1. So if you looked at this structure and you would say, this does not have enough electrons, this has too many electrons, I need to take some electrons from the aluminum and give them to this chlorine. This aluminum doesn't have any lone pairs to give, but the aluminum does have a double bond, which could be converted into a lone pair. So you could still use the formal charge. As long as you're using the formal charge, you're going to end up okay. You're going to draw the correct Lewis structure eventually. And let's see, we have 3 more that we can do. PCl5, phosphorus has 5 valence electrons. Chlorine has, we have 5 chlorine atoms. Each chlorine atom has 7, so that's a total of 35 for the chlorines, and overall total of 40 for the molecule. We're going to put phosphorus in the center. We're going to put all the chlorines around it. All 5 of them are going to fit around this. And that used 2, 4, 6, 8, 10 electrons. So we used 10 electrons to make those bonds. And now we're going to give the chlorine atoms their octets. They each need 6 more electrons. And we've got 5 chlorines. 6 times 5 is 30. So this is going to use up all of the electrons that we have. Now you might be feeling pretty uncomfortable to see that phosphorus with 5 bonds because that's kind of crazy. But again, we're going to calculate formal charges and see how things look. All of the chlorine atoms are exactly the same in this molecule. 7 valence electrons, 1 bond, 6 non-bonding electrons. All of the chlorine atoms have a formal charge of 0, so they are all perfect. Phosphorus has 5 valence electrons. This phosphorus has 5 bonds, no non-bonding electrons, also has a formal charge of 0. So boom, it's good. It looks great. Let's try SF6. Sulfur, 6 valence electrons. Fluorine, we have 6 fluorines. Each one has 7 electrons. That's a total of 42 electrons from the fluorines and an overall total of 48 electrons for the molecule. We'll put sulfur in the middle, and we'll just see what happens if we put all 6 of these fluorines around the sulfur. Formal charge is going to let us know if the sulfur can handle that. We used 2, 4, 6, 8, 10, 12 electrons to make those bonds. That leaves us with 36 more to go. We're going to work on the octets for the fluorines. Each fluorine atom needs 6 more electrons. Each fluorine atom has 1 bond, which means it's starting with 2, and we want to get it up to 8 electrons. There are 6 total fluorine atoms in the molecule. Each one needed 6 more electrons. That used 36. We have none left. For formal charge, all of the fluorine atoms in this molecule are bonded in the exact same way. They all have 7 valence electrons. They all have 1 bond. They all have 6 non-bonding electrons. They all have a formal charge of 0. Sulfur has 6 valence electrons, and this sulfur has 1, 2, 3, 4, 5, 6 bonds and no non-bonding electrons, so that sulfur is actually happy. Last but not least, we're going to draw the best Lewis structure for NO2 with formal charges as close to 0 as possible. Nitrogen has 5 valence electrons. Oxygen, we have 2. Each oxygen atom has 6. That's a total of 12 electrons for the oxygens and an overall total of 17. We want to put nitrogen in the middle with the oxygen atoms around. That used 4 electrons. We have 13 left. We want to start by giving the oxygen atoms an octet. Each one needs 6 more, so that's going to leave us with 1 more electron, and we'll put that 1 electron on the nitrogen. This is really a weird example. Let's calculate the formal charges before we do anything different. Oxygen, 6 valence electrons, 1 bond, 6 non-bonding electrons. That's a -1 formal charge. Same with this oxygen over here. 6 minus 1 minus 6 is -1. And the nitrogen, 5 valence electrons. This nitrogen has 2 bonds, and it has 1 non-bonding electron. That's a formal charge of +2. So remember, what we want to do is try to take electrons, I forgot the negative sign again, take the electrons from negatively charged atoms and move them into positively charged atoms. So we're going to take the electrons from this oxygen, bring them in here to make an oxygen-nitrogen double bond. That's going to change the formal charges on the oxygen and the nitrogen. 6 minus 2 minus 4, that's a formal charge of 0, so this oxygen atom is good. We shouldn't do anything else with it. And this nitrogen is 5 valence electrons, 3 bonds, 1 non-bonding electron. That's a formal charge of +1. Now, we could try to do it again. We could take another lone pair of electrons and move that in like that. And if we did that, that would bring this oxygen's formal charge down to 0, and it would also bring the nitrogen's formal charge down to 0 as well. But we're actually not going to be able to do that in this particular case, and I'm going to explain why in just a second. I'm going to put those electrons back. This is as good as we're going to be able to do with this particular structure. We're going to have a formal charge of +1 and a formal charge of -1. So let's take a look at a periodic table. When we're working on problems like this and we're violating the octet rule, there are some atoms, even though we see a lot of atoms violate the octet rule pretty freely, there are some atoms that are never allowed to have more than 8 electrons around them because they're just simply not big enough. And that's going to be all of our small atoms. So on the periodic table, working our way all the way over to as far as aluminum. Everything that is, that was just a really messy way to go about doing that. So everything up to aluminum is not going to be large enough to have more than 8 electrons around it. For all of these elements, you need to make sure that you are never giving them more than 8. Anything silicon or larger, you can go ahead and put more than 8 around it if the formal charges make sense. But all of the smaller elements, never give them more than 8. And that's why with this nitrogen atom, we can't move another lone pair of electrons in, even though that would be great for formal charge. The nitrogen atom, if we did that, would have 2, 4, 6, 8, 9 electrons around it, which is just too many. Nitrogen is not large enough to have more than 8.